There's a piece of pumpkin pie on this book. Now there's grease stains.
Use that as a plate.
Well, I was eating the pumpkin pie, but I had to do something, and then I just put it down in the book.
Why don't you just rip out one of the papers and take it?
Papers are valuable than the basic.
One paper is more valuable than the electronics. This is what people see when
Yeah, I don't care.
Okay. We were talking about intramolecular forces, and so what I just want to try and be as specific about as possible. When I say intramolecular forces mean forces inside the molecule holding it together. So here I've got a water molecule. This is what a water molecule kind of vaguely looks like. And what I'm curious about is there's an atom here, there's an atom here, and there's an atom here. Now as this thing is moving, right, it's screaming from one side of the room to the other, or from one side of a bottle to the other, right? It's colliding with other stuff. I'm curious, it's turning around, it's vibrating back and forth, right? This molecule is doing a bunch of different things. Why is it that this hydrogen atom doesn't fly off of that hydrogen atom? What's keeping them together with intramolecular force? Okay, thank you very much. So intramolecular forces are what's holding this molecule together. That's what we mean by intramolecular forces. So when I take a water molecule, right, this thing's sitting inside of a jar, inside of a beaker, and it's smashing up against the sides of the beaker, right? It's screaming around from one side of the room to the other. Sorry. I was aiming at Wim. I'm sorry. Okay? So I'm curious, what's causing it to be held together? Why are those atoms held together? It's an intramolecular force, but more specifically, what is this little stick that joins the two together? What is it representing?
electron.
It represents two electrons, and we call the two electrons in between them a bond. We call them, now specifically, what type of bond is in this molecule?
Double bond.
Is it a double bond?
No.
Sure doesn't look like a double bond to me. It looks like a single bond, right? But what's the name we give to this type of bond? It's a covalent bond. Why is this a covalent bond? Why is it different from an ionic bond? And I know that I'm using sticks here as well. That's a little bit misleading. Why is an ionic bond different from a covalent bond?
They share the electrons.
What was that, John?
They share the electrons.
Who shares what electrons?
They.
They, meaning which one? Left or right?
They.
Which one of these has covalent bonds? The molecule or the ionic compound?
Molecule.
The molecule, right? This molecule, these atoms are sharing the electrons between them, right? Sharing means co, and it's valent electrons, electrons in the valence orbital, right? How come this is not a covalent bond? Because it's ionic. What does that mean, Idris? Are they?
Oh, it's like a tug of war thing.
Yeah, and so in this tug of war, both people are still kind of battling it out, right? Both the atoms are still kind of battling it out. But in here, is the tug of war still happening? Not really. Somebody won the tug of war already. Somebody finished the tug of war. The negative ion already won the tug of war, right? So it stole an electron away from somebody else or from another atom. Does that kind of make sense? So that's the difference between an ionic bond. An ionic bond, the tug of war happened, somebody won it. Here, the tug of war is still going on. So when we have a tug of war still going on, if there's somebody here and they're trying to win the tug of, please keep in mind I'm terrible at this, okay, all right. If there's a tug of war still going on, are those two people bound together while the tug of war is still going on? Yeah, they're bound together by what? The rope. The rope is keeping them together. And if neither one of them is going to let go, then I guess they'll be stuck together for the rest of time. Does that make sense? Unless somebody wins that tug of war, which only happens in ionic compounds, hopefully that makes sense. That one was there, that one was there. If I'm tall enough. Yeah, try and see if you can throw it at me. Just watch out. Ah, that's pretty good. You got a better arm. Okay. So remember, this is the idea where the tug of war is still happening. One person's winning more than the other, right? Why is chlorine winning the tug of war? How do we know that chlorine's winning the tug of war? Yeah, it's more electronegative. What's the electronegativity of chlorine? 3.2. And hydrogen is 2.2, right? So yeah, one of these is winning over the other. What about in sodium and chlorine? What was the electronegativity here? 0.9 and 3.2. So what's the delta here? What's the difference? 2.3. Good. The delta is 2.3. Is this an ionic bond? How do you know, other than, it telling you, Stephanie, other than it telling you, how would you know this is an ionic bond? It's greater than 1.7, right? The difference is greater than 1.7. Okay, so we went through covalent bonds. There's two types, right? There's polar and nonpolar covalent. Then we talked about ionic bonds. That's where somebody wins the battle. Somebody outright totally won the battle for the electrons. Then there was metallic bonds. And then we started talking about, how do you say this? VSEPR. Please don't say VSEPR. Do you remember what this stands for?
Valence shell, electron, proton.
Valence shell, I don't know why I said share. Valence shell, electron.
Proton.
Patrick.
Parallel. No, you have to remember this. Oh, pair. Yes.
Oh.
Yes.
No, you don't have to remember this, but you might as well write it down.
I feel like
Oh, yeah.
Is it right there?
no, it's like right on the same page.
Oh, good. Oh, it's on the next slide. Oh, that's why I didn't see it. Woo. Okay. Okay. What we're gonna do on the circle. Do you guys have a circle here?
No.
Whatever. Okay. On the circle, we're gonna draw a circle. Draw one group of electrons on the exterior. Okay, sure, no problem. So I'm going to draw a group of electrons on the exterior. Now, it's the exact same thing as yesterday. Now we're going to draw a second group of electrons. Where are they going to go? If we added a second group of electrons onto this outside, the outside of the circle, it's going to go on the opposite side, right? And that should be really obvious. Why does this group of electrons, why do they not show up over here?
They're both negative.
They have the same charge, and they repel. That's absolutely right. And so these negative charges do not like being near each other. Here's the problem. There's no way for us to add a third group of electrons unless what happens? Yeah. So if I add a third group of electrons onto here, what are they going to do to these other two pairs of electrons? They get pushed down, don't they? Right? So if I have a third group of electrons, they get pushed down. Now here's the problem. If I add a fourth group of electrons, it's impossible basically for me to represent this on a sheet of paper. Would you agree it's going to be pretty hard for me to show how these get repelled? Yeah, we could use what's called stereochemical drawings. But I'm just going to show you this again, right? So we know for sure, if we've got two groups of electrons on here, right, they're on opposite sides, and hopefully by now we just immediately recognize a bond is two electrons. So I'm going to add another bond, and what did it do to the groups of electrons? It forced them down. Now, if I add another pair of electrons on here, another bond, I'm either going to add it from the top or the bottom, right? But either way, as soon as if I add it from the top, what's going to happen? These three get pushed down. So right now, are they all in the same plane? Yeah. They're all in the same plane, and that's what we mean when we say trigonal planar. If you only have three groups of electrons, if there's just three groups, right? 2 electrons here, 2 electrons here, 2 electrons here. If there's only 3 groups of electrons, you don't need to repel things down or up or anything like that. The furthest away they can get is all in the same plane. But the moment I add another group of electrons on top or on the bottom, these other groups are going to get repelled down, aren't they? And so let's see that in motion. I'm going to add another group of electrons. Doesn't matter if it's a lone pair or if it's a bond, right? I'm going to add another bond. I added it on the bottom, and all 3 got pushed to the other side. So you do have to memorize these names. This shape here, can you see that this is the exact same thing as that? It's just that I've added another group of electrons on the top. And by adding it on the top, right? By adding it on the top, those other 3 groups of electrons got pushed down. What is the name of this shape? Tetrahedral. Okay? So we're going to go through some things right now, and I'm going to pass these around if you want to get a better picture of them or get a better look at them. And we're going to do some examples, but let's mosey here. All right. Okay, VSEPR, valence shell electron pair repulsion, and it works exactly like the activity we just performed. According to VSEPR theory, only electrons of the central atom, they're the only things that are important for molecular shape, and it's only the valence electrons. Valence electrons are always paired up, right? You always see them in groups of 2. If it's a lone pair, that's 2 electrons. If it's a bond, how many electrons are in a bond? 2, right? So a bond is 2 electrons, a lone pair is 2 electrons. They always show up in pairs, so that's why we say electron pair. Bonded electrons and lone pairs are treated equally. They're the same, right? Do you think 2 electrons, doesn't matter if they're in a bond or a lone pair, are they still 2 electrons? Yes. So we're going to treat them equally. The molecular shape is determined by the position of the electron pairs when they are a maximum distance apart. So basically all that's saying is that you don't want 2 electrons to be closer than they have to be, right? It's like having a little brother, okay? You're never going to be closer to your little brother than you absolutely have to be at any moment in time. Would you agree with me? Yes, you are forced to be with your little brother all the time. Does that make sense? Because you are repelled by your little brother. He is a repulsive individual to you. Perfect.
Does that make sense?
Yeah, it definitely does.
What is the shape of the substance beryllium hydride? So we're gonna have to draw a structural diagram, and the structural diagram / Lewis diagram, that's what's going to help us determine the shape. Remember, if you have two pairs of electrons, if you have two things surrounding a central atom, they just want to be on opposite sides. Do you remember what that shape is called when there's just two things? They're in a line, right? They're linear. That's a linear arrangement. The central atom has electrons surrounding it in a line or in a linear arrangement. Okay, so let's try this out. What's the Lewis formula for beryllium hydride? How many valence electrons are in beryllium hydride? Yeah, let's count them up. Go ahead and count them up. It's a surprisingly small number. 4. 2 for beryllium, do we agree? And then 1 for each hydrogen. There's 4. Okay, well let's draw the Lewis formula for beryllium hydride. Here's beryllium. And remember, it has to be bonded to the hydrides. Now, are the hydrides going to be bonded like this?
No.
Does that make any sense? That doesn't make any sense. Why do those electrons, why are they not going to arrange themselves like that? Yeah, that's closer than they absolutely have to be, right? So I would put the hydrogen on the other side. Now let's count up all the bonding pairs. Let's count up all the lone pairs and figure out what the total amount of pairs of electrons. How many bonding pairs do we have here? 2 pairs. Do we agree? Yeah. How many lone pairs on the central atom? 0. So how many total pairs of electrons? 2. The general formula is what we call, this is embarrassing. I can't remember. I think it's AX2.
Oh, yeah.
A is just standing for like the central atom, and there's 2 sets of electrons around it. Okay? Is that all right? AX2. It's 2 sets of electrons. Is it on the next page?
Yeah.
Yeah. I should have put that chart first, but that's okay. Electron pair arrangement is linear. Okay, I want to prove to you that 2 sets of electrons, doesn't matter how it's arranged, 2 sets of electrons will always be this way. So I'm going to go back to that simulation. If I have 2 lone pairs, do you agree they set up in a linear fashion, all in a line? Even if it was a lone pair and a triple bond, do you still agree they're linear? Yes. Okay? So it doesn't matter, right? It absolutely doesn't matter at all. There's how many groups of electrons surrounding this thing? 1 group here, 1 group here. They will be in a linear fashion. When?
Why is that one on like a curve or angular thing?
We're going to talk about that. Is that okay? Yeah. We're going to talk about that. Kylan. Why you're going to ask why H2O, it has 2 bonds, right? Well, why the hell is it not linear? We'll figure that out in a second. Is that okay? Some people are probably already there, and that's totally fine. Okay, what is the shape of the substance BH3? So count up all the electrons in BH3 for me. It's not 4.
It's 5.
There has to be an even number, right, Idris? It's 6, right? So boron is 3 and hydrogen is 3 each, right? So that's 6. So how is this going to be arranged? The Lewis formula. Oh, sorry. We never actually finished the stereotypical. This is, so that's my fault. It's just BE with 2 hydrogens on the sides. All in a line, right? Not bent, not angular, anything like that. Okay, I don't want to get ahead of ourselves, but beryllium is going to be in the middle. Sorry, boron's going to be in the middle. And what's going to be surrounding it? The hydrogens. Now, some of you are ahead of me, probably. I'm going to put them like that. Okay, do you immediately know there's something wrong with this? Yeah, but this is the Lewis diagram, and I'm fine with you just doing it like that. Okay, how many bonding pairs are there here? How many bonding pairs? 3. How many lone pairs around the central atom? 0, so there's 3 total pairs. So this is what we say, there's a single central atom, and it's got 3 things around it. So the electron pair arrangement, what's the name of 3 things all in a plane? Trigonal planar. Yeah, it's kind of looks dumb. I'll give that to you, but so I'll put a B to show the stereochemical formula. I'll put a B, and all I have to do is put H's and try and make them so that they're all spread out evenly apart. I want to be very clear. It's fine when you do your Lewis formula, if you jump to that arrangement, that's totally fine. But I just want to show you that this is okay. A Lewis formula does not have to show the arrangement. Okay, perfect. What is the shape of substance CH4? Well, let's do the Lewis diagram for CH4. Some of you are ahead of me, and that's fine. How many electrons in CH4? Jana, did you just say 8? Why? You're correct. Why is there 8? How many does carbon have? 4, and there's 4 hydrogens, right? 4 plus 4 is 8. So carbon in the middle, hydrogen on the outside. By the way, what's the name of this thing? What's the name of CH4?
Ammonia.
It's not ammonia. It's
Ammonia.
methane. Right? It's methane. Okay, whatever. How many bond pairs are here? There's 4 bond pairs. How many lone pairs are here? 0. So how many total pairs of electrons? 4. So the general shape is AX4. Now this electron shape, right? When I do this, if I add 4 pairs of electrons, do you remember what the name of this thing is? Tetrahedral. And the reason why it's named tetrahedral is I can make 4 faces on here. If I were to, do you know, like if this was the skeleton of a die, like dice, do you know what I mean? And if I covered it in like saran wrap, there'd be a face here from these 3 atoms. There'd be a face here, there'd be a face here, and there'd be a face here. Okay, so there's 4 faces on here. They make tetra 4 faces hedral. That's the idea behind it. So we call it tetrahedral.
It's so pretty.
It's 40.
No, it's not.
There's 4 sides.
The stereochemical formula, now please do not freak out on me, okay? It's really easy to draw. It's really easy to draw 2 of these hydrogens in the plane of the paper. Okay? So this hydrogen and this hydrogen, it's like if you had a sheet of paper that cut it down the middle, this hydrogen and this hydrogen are in the sheet of the paper. But is this hydrogen out in front? Is it in the plane of the paper? No. Is it coming at you or is it going behind? It's coming at you. And so the way we represent that it's like if I had a stick here, and I don't, so this is whatever, this is, you just have to imagine it. If I had a really long stick, yeah, I know, but that, I don't know, yeah, okay, sure. If I had a stick, okay, and I pointed it at you, John, okay, is the, no, okay, is the part of the stick that's closest to you or furthest away? Which end looks bigger to you?
This end.
That end looks bigger, right? So if I had a bond, right? A bond is just like a stick of wood almost. Because this hydrogen is closer to you, it looks bigger. So we draw, it's like a wedge that's facing towards you. Does that kind of make sense?
No.
No? Okay, wow, that's too bad. And then this is probably, I don't know, this is really going to blow your mind. The one that's going behind the plane of the page, we draw as a dashed line. Just deal with it. I'm not making this up. I promise. Stephanie, am I making this up? No, I'm not making this up.
Where's your chemistry
What?
certificate?
I'm just a crap artist. That's all it is. Okay. So I could have drawn it a little bit better. It should be like it should be like a wedge, but it's a dashed wedge.
I just draw like a.
That's the way you'll see it. You'll see it as a dashed line like that. Okay. What is the shape? Yeah, that's dumb. That's dumb. But we're going to do it. Okay, what is the shape of the substance NH3? So let's draw the shape of NH3. How many electrons in NH3? 8. There's still 8 electrons, right? Okay? So I'm going to put my N, and I'm going to put my hydrogens surrounding my N. Okay, I'm used to putting them on the sides and the bottom. So I'm going to bond them together.
Methanol.
No.
So I've got 6 out of my 8 electrons done so far. Where am I going to put the other 2 electrons? The top of the end. Do you agree they can't go on the hydrogens? Because hydrogen's already full. So they got to go here. So now, how many bonding pairs are there? There's only 3 bonding pairs. How many lone pairs are here? There's 2 electrons, but it's 1 pair of electrons, right? Okay. How many groups of electrons in total are surrounding it? 4, right? So would you agree it's going to look exactly like the tetrahedral one, except is there an atom on top? There's no atom on top, so you can't see it. So what shape does this make now? You can't see the atom on top. This is trigonal, but is it in a plane? Are they all in the same plane as each other? This is trigonal, pyramidal. Let's make it on our dealie here. Okay, how many bonding pairs were on this thing? 1, 2, 3. Okay, and how many lone pairs were on here? 1. So when I look at this, so that's what it looks like, except you can't, I want to be very clear, you can't see electrons. We can interact with atoms, we can see atoms kind of, okay? But you can't see electrons. So I'm going to ignore the lone pair because you can't see it. So does it still kind of represent something tetrahedral? It's just that thing is missing up here, right? It's not missing, you just can't see it. It's a lone pair. So can you see how this is trigonal? There's 3 atoms surrounding it, which makes it trigonal. But is it planar? Is it all in the same plane? No, it's not trigonal planar, it's trigonal pyramidal. Do you see how it's kind of making a pyramid? Yeah. So that's what this is. This is the shape of ammonia. I'm too short. So this is the shape of ammonia. Why are these 3 bonds bent down? What's the reason why these 3 bonds here are bent down, Wim? There's a lone pair on top that must be forcing them down. Does that make sense? So hopefully you kind of recognize that this is the exact same thing as tetrahedral, right? It's the exact same thing, except you just can't see the top. Because there's only electrons, there's no actual atoms there. Okay, so the total pairs are 4. There's still 4 sets of electrons, but one of them you can't see. So we're going to call it AX3. What that means is there's surrounding my central atom, how many atoms are there? 3, and there's a lone pair of electrons around it. There's still 4 things, but one of them you can't see, so we call it trigonal pyramidal. Okay, let's draw this the exact same way we drew the tetrahedral. So what's in the middle? What atom is in the middle? N. And you still have a hydrogen, but 2 of the hydrogens, one's coming out of the page and one's going into the page. Now I want to be super clear. I don't think I'm ever really honestly, truly going to assess you on stereochemical drawings. This is something that at the university level they're going to hammer into you in organic chemistry and things like that. But stereochemical drawings at the Chem 20 level, it doesn't go anywhere in Chem 30, so I don't really care about it. I'm teaching you, but I'm not really going to assess you, as long as you understand. The name of the shape is much more important. Okay, we got 2 more. We got 2 more. We got 2 more. Here we go. Yes. You gotta go. Okay, what is the shape of the substance H2O? Well, we already know what it is, right? You've been drawing H2O for years now. What shape is it? Is it linear?
No.
It doesn't look linear. It's like you took something linear and then you bent it. So can we call it bent?
Yes.
Let's call that bent.
Yeah.
Sure, bent. What's the other name? Angular. Sure. Bent angular. But if you say benangular, it's wrong. Lewis formula. Okay. How many electrons in water? How many valence electrons? No. There's 2 hydrogens, right? So that's 2 plus the 6. So that's 8. So let's draw this. O H H dot 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 dot. So I'm done with 4 out of my 8 electrons. Where are the other 4 electrons going to go? Yeah, they have to go around the oxygen. They can't go around the hydrogen. They have to go around the oxygen. Okay, how many bond pairs are here? I see 2 bond pairs. How many lone pairs? 2. So how many total? 4. So what do you think the general formula is going to be? AX2E2. Okay, this is still a tetrahedral-like relationship, okay? let's see what happens when we put this into the simulation. Okay, how many bonding pairs? 2. How many lone pairs? Whoa. Sorry. Remove all that. Yeah, good. Okay. 2. So if it was just 2, it would be linear, right? But how many lone pairs are on here? Do you see that? And if I turn the lone pairs off, what shape does it take on? Bent, angular, angular bent, angular bent, whatever, it doesn't matter, okay? So, do you understand, if something is not linear, there must be something forcing it to be not linear. Now, in the case of water, right? This is the shape of water. This is what we see. We see the atoms, or we can interact with the atoms really easily. What's forcing the bonds to be closer than they absolutely have to be with each other? There's 2 lone pairs on top. There's one here and there's one here, and they're forcing them closer than they want to be with each other. So we call this angular or bent. One of them sounds a little bit more, high class. One of them sounds a little bit more blue collar, and that's totally fine. We accept both around here. The stereochemical formula, this is awesome. You don't need any wedges or dashed lines or anything like that, because everything can be in the plane of the page, right? Everything can be in the plane of the page. Nothing's coming out at you, nothing's going back in, something like that. Are we okay with that? And then the last one, what's the shape of HF? Bend. There's 8 electrons, right? So F, and there's an H there. That's 2 out of my 8 electrons. Where's the other 6 going to go? How many bond pairs? How many lone pairs? How many total pairs? What's the general formula? The electron pair arrangement, well, this is tricky. This is honestly really tricky, because you have one thing. I mean, how many different shapes can you make out of 2 points?
Linear. A lot.
Yeah, it's linear, right? It's not even really linear. It's nothing. The central atom has no shape. There's an arm coming out of the central atom. It doesn't matter which way you point the arm, right? It's always going to be linear. Are we okay with that? Yes. All right. Stereochemical formula HF. What are the only 2 shapes that really show up with stereochemical formulas? What are the only 2 electron pair arrangements that show up? It's just the tetrahedral and the trinopyramidal, right? That's the only time you ever have to worry about it. But again, I'm not really going to assess you on it. I don't really care. So this is just like a diagram for you to be able to kind of take a look at it real quick, right? I understand that they did the dashed line like a but some other, that's fine, whatever, it doesn't matter. Okay? Okay, what I would like you to do, what I would like you to do is try these 2 examples, please. Try these 2 examples. And if you finish them in the next 5 minutes, I want you to try working on some of these, okay? You don't have to do question number 1, even though you could. just read it backwards, right? VSEPR, the repulsion of electron pairs of the valence shell, blah, 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 blah. So you're doing these two, please. Thank you.
Never a pen or a pencil.
Did I not? I didn't. Okay, I'll do that. Yes.
Wait, I can?
Yeah, I might not answer it.
That's what I wanted to answer.
Okay, well, one.
I want it.
I was still confused.
Okay.
So I did all of these three. And are they wrong or correct?
Yeah. Well, so this is good. That's good. That's good. That's good. That's good. That's not. That's interesting. There's a big difference between one and the other. Yeah, it's still an ion.
Dot E.
And then this one's wrong.
I don't know.
Okay. Then I'm good.
Now you just need the VSEPR shape, right? You just need the shape of the central atom.
I did not actually.
Did you say? I don't know. No. I'm just messing with it. I'm not right.
The major assignment is due on Monday, correct?
Yes.
The major assignment is due on Monday. Yeah. Yeah, that's yeah, okay. You have it. You missed it.
I need to get up and
3 days ago. I completely understand. That makes a lot of sense. So, there's no point in me really explaining this to you right
on an exam.
I see that. You see what I see? It's double, triple bonded. It's triple bonded. That's the only way you can make it okay.
Because I think
If it's single bonded, it didn't work. I think this next Tuesday.
Well, yeah, 4 times.
That's 32.
okay.
16, 18.
But this works too.
Yeah, I suppose it's
Wait, does it? 12, 18. That's my first. No, that's so good. And only hold 16. But what is this shape?
No, we said everything was right. We said everything.
Wait, how do you like this?
Just do the whole thing. Do all of these.
It's not doing that. But how do you figure out the shape, the electron? Oh, it's natural.
Yeah. Good. Good. Yeah. No. So many. How many electrons are surrounding the sulfur?
24.
Well, how many can sulfur carry?
16.
8.
8? What?
How many in sulfur's row?
8.
There's 8 things in sulfur's row, right? So it can hold a maximum of 8 electrons. Okay. We're going to do this together. Is that okay? Shh. So just listen up. So predict the shape of the sulfate ion. A sulfate ion is SO42 minus. Do you agree with me on that? All right. So SO42 minus, we're going to count up all the electrons. I don't want to do that in detail every time. Trust me when I say there's 32 electrons.
Yes.
Why is there 32 electrons? This is 30 and 2 extra electrons, right? So there's 32 electrons. So let's draw SO4 with 32 electrons. SO4. That's 8 of my 32. I've got 24 left over. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Boom. All 32 electrons are done.
No, it doesn't. It doesn't have a
Okay. Is everybody happy?
Yeah.
Are all the atoms happy in this entity? Everybody's at max capacity, right? So you cannot backfill. We've run out of electrons. You cannot backfill. So this is the Lewis. This is the Lewis diagram for sulfate. But that's old news. Nothing new here. How many bonds are surrounding this sulfate? There are 4 bonds. So what shape is this going to be? This has to be tetrahedral. Do we agree with that? Yeah, 4 atoms surrounding this is going to be tetrahedral. So we'll go now, I haven't actually answered the question. I haven't physically answered it. The shape of the sulfate ion is tetrahedral. But I just want to make sure we're on the same page. That's the way you would draw it, right? Predict the shape of carbon dioxide. How many people have actually finished that? Yeah? Okay, do we need a little bit more time?
Yes.
Okay, I'm going to give you 2 minutes while I hand something out.
You gonna wash it?
Yeah.
I did what? No.
How it was in
Wow, so much work. How do you feel this? Oh, okay.
I just told my mom I was at 60. And in grade 10, but now I was Saturday.
Okay, I'm going to give you 30 seconds to finish it off. Yeah, what are you going to go first? The peripheral or the central? No.
Oh, right. So they can't be. No, yeah.
Thank you, Maddie. I did not look back.
No more electrons.
I feel bad.
So how are you going to do it?
Let me see.
I think it's right.
Does it have extra electrons or not enough electrons? Are electrons negative or positive? Electrons are negative. Oh, if you're too negative, that means I've got 2 extra electrons. So you have to add 2. Okay. So, carbon dioxide. If you haven't already done it, please just trust me that it's 16 electrons. So carbon dioxide. Now, what are the 2 options here? It could either be linear or it could be, what's the other shape that 2 atoms can make?
Angular.
It could be angular bent, right? Two peripheral atoms. So we don't know, but let's try and find out. We've got 16 electrons, so 2, 4. What do you want to fill in first, the peripheral or the central? The peripheral. 6, 8, 10, 12, 14, 16. Okay, I'm done. I can't add any more electrons. Are all of the atoms fulfilled? No, they're not. Carbon doesn't have a complete octet, so what can I do about this? I can erase some of these bonds, or erase some of these electrons, and I can make double bonds, right? So this is CO2. What shape is this going to make? It's going to be how many groups of electrons are there surrounding this C? I see 4 bonds, but this is a group, right? This double bond, wherever half of the bond goes, the other half has to go, right? So wherever this double bond goes, and wherever that double bond goes, they want to be opposite of each other. This is linear, right? It's all about visualizing in your mind what's going on. Okay, I want to take 20 seconds and just let you know that we're if I wasn't gone on Friday, we would be perfectly on time. We would be perfectly on pace, okay? But since I'm gone on Friday, and I know the name of the guest teacher, but I have no clue how comfortable they are with chemistry. So we're going to try, well, the name's in my email, I don't know, but I've never heard of it before. Maybe I've seen this person before, but I don't know. So as long as you promise not to react badly when you hear. Okay, I don't know if it's Miss or Mrs., but Miss or Mrs. Pet Cow.
Stop, you said that to react.
I've never heard of it.
Okay, now that sounds weird. I'm not saying pet cow.
Oh.
Hey. Does anybody know who that is? Pet. Is that not how you would pronounce P-A-E-T? Pet? Pat?
I don't know.
No, I'm good. Okay, so what I'm trying to say is that if I was here on Friday, we would be perfectly on time with where we need to be right now. But I don't know how comfortable they are. So I would normally give you time to work on this. But I'm trying to jam in as much of my personal instruction as I possibly can in the next 2 days. And then Friday is going to be like a work day. Is that okay? As best as we possibly can. Now that means that you just have to trust me when I say there's no time for questions. We've got to move on to something else. And that's what we're going to do right now. This, I will put the key for that sheet that I literally just gave you. The goal of this is Lewis diagram, structural diagram, right, with stereochemical drawings. But most importantly, what? That last column. Tell me the shape of the central atom. That's the most important thing, okay? I want to move on. We're going to do a little bit more of this as we go on today and tomorrow. So trust me, it's not just going to go away. We are going to practice it. But I'm going to put the key for that on Google Classroom tonight. It's not due for marks. Do it. Don't do it. It's all the same to me. Okay? I'm going to give you a quiz just on molecular shapes. That's the only thing that's going to be on the quiz. Just on molecular shapes on Friday. Is that okay? And if you do poorly on it, you can rewrite it on Monday, but at least you get a little bit of feedback. You get a little bit of feedback on it.
Copies later.
Yeah.
It's going to be online.
Here.
I should have done that.
What do you mean?
Did you know?
This is the last booklet I will hand you in Chemistry 20. What? Yeah, you're redoing it. Yeah, I'll give it to the. I'll have it out here in my subclass, and you can just come here. It'll be.
What is that name?
It's so big because there's pictures in here. You gotta draw lots of that.
I don't know why you're next year.
What? There's only 10. Jump.
Shapes. So if you need to draw a structural diagram, I got no problem. Shape is what I do.
Is there a negative charge? C is 4H plus 100 complex.
And then there's only 10 years. Oh, probably on the other side. No.
Okay.
Right? That's fine.
So think back to yesterday and earlier today. What does it mean when I say polar, instead of polar molecule, polar, what have we just talked about? Polar covalent bonds, right? So remember, a polar covalent bond, we know about them, we know about how they're formed, and we know that in order to have a polar covalent bond, what does the electronegativity have to be?
A positive.
Right? And remember, an electronegativity of 0.1 or a difference of 0.1 or 0.2, is that really a big difference? No, so we can kind of ignore those, right? By way of an example, we could talk about the hydrogen. I don't want to talk about hydrogen chloride. Hydrogen bromide. What's the electronegativity of hydrogen? 2.2. What's bromide, bromine? 3.0. So what's the delta here? 0.8, right? So is this a polar covalent bond? Yes, this is. So what I wanna think about, okay? If we were to draw the electron cloud, if I were to draw the electron cloud around HBr, who owns more of the electrons? The Br. So it's like, remember, it's, does that kind of make sense? I tried to make it wider around the Br because the Br is pulling it. Now, that's not the only way, the only way we can indicate to you that the Br is hogging the electrons. What's the other way we can do this? With the tiny delta negative and tiny delta positive. And I'm actually going to introduce a third one to you right now. Okay? Which direction are the electrons getting pulled? Yeah, towards the Br, right? So what I want to do, sorry, are the electrons getting pulled to the right or to the left? Right. That's how I can show you that there is what we call a dipole in this molecule. So the electrons are getting pulled towards the bromine, and this is an arrow, and I drew a little plus sign on the one side. Why did I draw a plus sign on the one side? It's the more positive side, right? Are we okay with that? So there are three ways I could indicate to you that a bond has polarity. Delta negative, delta positive. I could put a cloud of electrons, or probably the most common way to show it is by doing the arrow, with the plus sign at the positive end and the arrows pointing towards the negative end, pointing towards the side where it is. Okay. So how does this affect the molecule as a whole? So let's think about this. Is HCl a polar molecule? Let's look at the molecule as a whole, and let's see. Does it have a positive end? Does it have a negative end? What do you think?
Negative.
HCl. Like, no, what? If it's got a negative end, it has to have a positive end. Would you agree? Yeah. So is it going to be positive on one side and negative on the other? Yeah, I think so. The structural diagram of HCl is just HCl. So what's the shape of the molecule? It's linear. Would you agree with that? There's only two ways you can arrange or only one way you can arrange two objects. They just have to be in a straight line all the time. So this is linear. Draw the bond dipoles of the molecule. Okay, that's no problem. HCl. Which side is more positive and which side is more negative? You figure it out for me.
Right side.
Yes, this is 3.2, right? This is 2.2. So where's the arrow pointing? Is the arrow pointing towards the chlorine or towards the hydrogen? Towards the chlorine. Okay. Is the molecule as a whole, this whole thing is a molecule, does it have a positive side and a negative side? Yeah, so this is a polar molecule. Remember, the Earth is polar, right? Why? How do we know the Earth is polar? It's just two poles. It's got a north and a south end, right? How do we know this is polar? It's got a positive and a negative end, right? That's all polar means. It's got one side positive and one side negative. Okay. Is carbon dioxide polar?
No.
Let's draw the structural diagram for carbon dioxide. Well, in order to do that, we have to draw the Lewis diagram. CO2. How many electrons? 16. So CO2. If there's 16 electrons, I've used up 4 already. So 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Yeah, we got to double bond this, right? We did this about 10 minutes ago, but I just wanted to make sure we understood this. So we're going to swing down these bonds here, swing down these bonds in here. So the structural diagram is going to look like this. C, double bond O, double bond O. Now, what is the shape of the molecule? Linear. Draw the bond dipoles on the molecule. Well, let's look at each bond individually. The first bond, what's the electronegativity of the O? 3.4. What's the electronegativity of the carbon? 2.6. And then just for fun, we're going to put the other one here, okay? This first bond here, the first CO double bond, does this bond have a positive and negative side to it? No. This bond is there one of these atoms? Is one of these atoms kind of stealing more of the electrons? Yes. Which one? The oxygen. So where is my arrow going to point? Now let's look at the other one. Okay. Let's look at the other side, and what do you kind of intuitively know about the other arrow? It's pointing the exact opposite direction. Would you agree? So, what I want to ask you is, overall, does this molecule have a positive end and a negative end? No. It's got like a more negative side here. It's a little bit more positive in the center, but it's a little bit more negative on the side. It's not polar. Would you agree? There are not opposites on opposite sides. The way you think about this arrow is a vector. Do you remember back to Science 10 or anybody taking physics? Yeah. If I go this way, then this way, then this way, then this way. What's my displacement? It's 0, right? My displacement is 0. If I add up all of these vectors, it's 0. So if I add up a vector that's going to the left and a same size vector that's going to the right, if I add them up, what happens? They cancel each other out. This is what we call, what do you think? Is it polar or is it, no, not bipolar, non. This is non-polar because the bond dipoles cancel out. The bond dipoles are going exact opposite directions and they're the same size, so they just cancel each other out. This molecule is completely non-polar. Is that okay? That's where we're going to leave ourselves with this idea of polar or non-polar in a molecule.